Hello. We have a question here from G Advanced 2024, paper 1. It is a multiple choice question with a single correct answer. The concepts involved are basically the concept from rotational dynamics, and it also involves ideas from collisions. So we look at the question directly. A bar of mass capital M is equal to 1 kilogram and length capital L is equal to 0.2 meters is lying on a horizontal frictionless surface. One end of the bar is pivoted at a point about which it is free to rotate. A small mass, small m is equal to 0.1 kilogram, is moving on the same horizontal surface with 5 meters per second speed on a path perpendicular to the bar. It hits the bar at a distance L by 2 from the pivoted end and returns back on the same path with speed v. After this elastic collision, the bar rotates with an angular velocity omega. Which of the following statements is correct? Now, we look at what happens before and after the collision using this figure here. So this is what we have. The particle small m of mass small m is traveling with velocity v0. It is approaching the road, and the road at that instant is stationary. After the collision, the particle returns back in the same path, and the rod starts rotating with an angular velocity omega about this point here, this pivot here. Now, so before we'll basically start with the angular momentum conservation, L vector conservation here, and we'll do that about the point O. So about the pivot is the angular momentum conservation applied here. So now, before the collision, the angular momentum of this particle here about the pivot would be basically its linear momentum multiplied with the perpendicular distance between the direction of motion and the point about which you're calculating the angular momentum. So basically you have mv0 multiplied with L by 2. And I would say that I would consider this angular momentum here to be positive because you have r vector here and p vectors here. R cross p will be in the direction that is marked by perpendicular to this plane outside it. So I would choose that direction to be positive. So I'll just keep it as positive. Now, after the collision, before the collision, the angular momentum of the system is purely the angular momentum of this particle here because the rod is stationary. Now, after the collision, the angular momentum of the system here will be the angular momentum of the rod about point O plus the angular momentum of this particle about the point O. Now, angular momentum of the rod about the point O here will be simply I omega, where I is the moment of inertia of this rod about this axis here, perpendicular axis here, passing through point O, and that you know is m L square by 3, and that multiplied by omega will be the angular momentum of the rod about this point O. That is simply I omega. Now, since omega is anti-clockwise, I would have that angular momentum in a direction that is perpendicular to this plane towards you or outside the plane. That again is positive conventionally here for this question. Now, that and the angular momentum of this particle here after the collision here would be basically mv, its linear momentum multiplied with L by 2 again, but that will be a negative value because you have p vector down here, r vector is here, r cross p will be into the plane. So if out of the plane is positive, into the plane will have to be negative. So I have minus mv into L by 2 here. All right, on rearrangement, what I would then have here is simply ml by 2 into v plus v0 is equal to m L square omega by 3. We'll keep that here. And now, in the question, it is very clearly mentioned that the collision is perfectly elastic, which means E, the coefficient of restitution here, will have to be equal to 1, which means the ratio of relative velocity of separation to the relative velocity of approach has to be 1, which means the magnitude of relative velocity of approach will have to be equal to the magnitude of the relative velocity of separation. Now, how do we find that out? Initially, while the approach is happening, the rod is stationary, just the particle is moving. So relative velocity of approach will simply be equal to v0. Now, after the collision, the ball is traveling, the particle here is traveling with v downwards, and the center of mass of the rod will be traveling upwards here with a velocity given by L by 2 into omega. It's simply v is equal to r omega. That's what you're using here. The linear velocity of this point here, this center of mass here, will be simply the product of angular velocity with the separation here about point O. So that is what we have here. So basically we have the velocities, the individual velocities in opposite directions. So the relative velocity will be the sum of those individual velocities, which is basically v plus L by 2 into omega. Please remember that the velocity of the center of mass here for this rod would be L by 2 into omega, and that will be the upward direction. And the particle has a velocity v in the downward direction. The relative velocity will be here. Right? Now, on rearrangement, I would have omega is equal to 2 into v0 minus v divided by L here is the equation 2. I'll substitute equation 2 in equation 1 here. I'll call this equation 1. So 2 in 1 would give me ml by 2 into v plus v0 is equal to ml square by 3 into omega here is 2 by L into v0 minus v. Now that would then result in cancelling off L square and both the L's from the other side, from either sides. And then you'll have, you know that m is 0.1, that is given in the question. And capital M is simply 1. So if I cancel those figures out, I'll still get 10 here on the right side, which makes it much more simpler. I have v plus v0 divided by 2 is equal to, I have here 10 after the cancelling off, and then I have 2 by 3 here along with v0 minus v. So I have 20 by 3 into v0 minus v. Now, we'll try solving this. You know that v0 is 5, that is given in the question. So we have basically v plus 5 multiplied with 3 on cross multiplication. That will be equal to 40 multiplied with v0, that is 5 minus v here. Try and simplify this by opening the brackets. It's 3v plus 15 is equal to 200 minus 40v, which would then amount to 43v is equal to 185. You divide this, v will be simply 185 divided by 43. That will be approximately equal to 4.3, slightly more than that. Now, we've just got v here. We need to find omega. We'll go back to this equation here. Omega will be equal to 2 divided by L into v0 is 5 and v you already know now is 4.3. That would amount to omega is equal to 2 is right here divided by L is 0.2, that is given in the question. L is 0.2 here. So 0.2 multiplied with 5 minus 4.3 is 0.7. And this is basically 10 into 0.7, that is approximately 7. Now, since we have used an approximate value here in place of v, this answer will also be close to the actual answer. So we look at the options here. V has to be equal to 4.3 and close to 4.3, and omega will have to be equal to a very close to 7. The correct answer would be 6.98. The closest answer would be 6.98, and that is how we solve it. The correct answer is option A. Omega is 6.98 radian per second, and v, velocity, is 4.3 meters per second. That's how you solve it. We are using the basic principles here of angular momentum conservation and the idea of collisions here. Now, there is a tendency to use, there could be a tendency to use energy conservation here because the collision is perfectly elastic. We'll try and sometimes you may try and equate the total kinetic energy before the collision with the total kinetic energy of the system after collision to solve this question. It is conceptually fine, but the problem there is that the simplification, the mathematical simplification becomes all the more complex. You will find it really hard to get to the answer, but this is actually the most simple way of doing this question. I hope you understand how the solution is done.